السلام عليكم ورحمة الله وبركاته. Let's move on from where we stopped in our previous class. Of course, I have updated the slides. So after the class, I will upload the updated slide on the Blackboard so that you can access it. Okay. In our previous class, we were discussing about calculating the pressure force on a curved surface. Here we said when the curved surface is above the liquid, like in this case, you can see the curved surface here above the liquid. Okay. The weight of the liquid and the vertical component of the hydrostatic pressure or hydrostatic force act in the opposite directions. Okay, hence here we subtract. Okay, because force is a vector component. And then when the second figure, when the hydrostatic force is acting on a circular face, the resultant hydrostatic pressure passes through the center of the semicircle. Okay, because any point that is perpendicular to the semicircle surface has to pass through the centroid of the cycle. Then this is a situation whereby you have a plate. This is the length of the total length of the plate, B1 plus B2, but then immersed in two different fluids, oil and water. Okay, so definitely the hydrostatic pressure distribution will be different. Hence, we need to find the resultant hydrostatic force in each fluid and then add the two up to get the overall resultant. Okay, this is for water, which is denser than oil in this case, so it will the hydrostatic pressure force will be higher than that in oil. Okay, so we find FR1 and FR2 using the previous principles that we explained and highlighted before, and then at the end we sum these two up. Okay, this plus this to give us the overall resultant hydrostatic force acting on the plate. Okay. Now, for the curved gates, we explain how to do it. Okay, we'll take example. All we need to do is to divide the applied forces into horizontal and vertical. Okay, horizontal acting on the fluid element, then this volume. Okay, this is fx, and this is fy. Okay, and then from here, once we find fx and fy using all the previous principles we highlighted, okay, this will be the distribution for the vertical. It will be this, which is more or less constant acting through the centroid. Okay, so we can find the resultant. Okay, we can find the resultant hydrostatic force acting on the fluid element. Okay, and the angle through which it course, that's its direction. Okay, so let's take an example to demonstrate the application, how to find the hydrostatic force on a curved surface. Okay. Yeah, this is exactly for the horizontal one, we use this. The vertical one, which is simply we use the weight, okay, the unit weight times the volume. Now, in this example, we have a surface. Surface AB is a circular arc with a radius of 2 meters. Okay, so the radius of this arc AB is 2 meters and a width of 1 meter into the paper. So it has a width of 1 meter into the paper. So in actual sense, it looks something like this. Okay. So the width, this is the width, is 1 meter. Okay. the radius of the arc is 2 meters. Okay? Now the distance EB is 4 meters. This is the depth from the water surface to the top of the curved surface, which is 4 meters. The fluid above AB is water. Okay, and atmospheric pressure prevails on the free surface of the water and on the bottom side of surface AB. So you have hydrostatic atmospheric pressure acting here, as well as here. Okay, and it's no need to include their effect will cancel out. Okay, and question says find the magnitude and line of action of the hydrostatic force acting on surface AB. We want to find the magnitude of the hydrostatic force F here acting on surface AB. Okay. We want to find the force and the line of action. That's why it passes through. Okay. Now, in this case, we have water which is contained by a curved surface, and we want to find the hydrostatic force as well as line of action. Hydrostatic force. A line of action here simply we want to know the direction. Okay, the direction of the hydrostatic force. Okay. And how do we do that? These are the steps. Okay, you have to apply equilibrium concepts to the body of fluid, ABC, and that is why, like I always mention, statics is a prerequisite to this course. You need to understand statics, basically the generation of free body diagrams from problems, as well as the application of the equilibrium equations to such figures. So we need to find the horizontal component F by applying equation 3.34, and we find the vertical component also by applying the relevant equation, and we find the line of action of the force as well by using graphical solution, which we are going to explain below. So the force in the horizontal direction, okay, is simply the area acting at the centroid times the pressure acting at the centroid times the area, okay, which is, P bar A. Okay, so this pressure P bar is acting at the centroid of this phase. Okay, the force, the pressure distribution is this way, but P bar is acting at the centroid. Okay, this is where P bar is acting. Okay, so that's why here we will, if it's this should be the center. So definitely this depth, this is 2 meters because the radius of the curve is 2 meters. So the centroid will be at 1 meter. This is 1 meter below C. So from the top of the water, that is 1 plus 4, which is 5 meters. So the pressure, the resultant pressure will be acting through the centroid, that is at a distance of 5 meters from the top of the water. Okay. Then the area pressure is rho GH, okay, or gamma H. So P bar, simply the height of water acting, okay. So gamma H, so this is gamma, and the area of the curved surface, which is 2 times 1, okay. So this gives the pressure in the hydrostatic force in the X direction. Now, on the vertical direction, is also similar, okay, except that the distribution, the pressure distribution here on the vertical direction is uniform in this case. Okay, this is the pressure distribution, which is uniform. So it's simply the pressure also at the centroid, okay, times, and the pressure acting here is also gamma H. H in this case is 4 because the distance from the top of the water to this point is 4 meters. So that's why you have 4. Okay, and this is the unit specific weight of water. Okay, and the area still remains the same, 2 times 1. Okay, and then we need to find the weight component. I mean, the weight of the fluid enclosed by the curved surface, okay, which is given by, the specific weight times the volume ABC, okay, and the volume ABC. And how can we find the volume ABC? The volume ABC, this is not a semicircle, it is an arc that is 1/4 of a cycle. So that's why we have, it is simply the area of the quarter of a cycle times the width. Okay, so simply the area times the width. Okay, so here we have the area of cycle is pi r squared. Okay, this is an arc which forms 1/4 of a cycle, so the area will be 1/4. And then the volume we multiply by the width. Okay, that is how we obtain this. This gave the weight of the fluid element acting on the on BCH. Okay. Then having obtained all the forces FH, FV, and W, the rest is the application of equilibrium equation. So summing for the vertical component, we have Fy plus W, okay, which from the vertical component of the force, and then the line of action, of the center of pressure. The line of action of the center of pressure is given by the formula YCP equal Y bar plus I bar over Y bar A. Okay. Y bar, as we know, is from the top to the centroid, which is 5 meters. And then I bar, which is the moment of inertia, is BD cubed over 12. Okay. BD cubed over 12. Okay. Which is exactly what we have here. And then you have Y bar, which is also 5. And then the area 2 times 1. Okay. So that gives the center of pressure. And then the line of action, or where the center of pressure is acting, okay, this YCP is below the centroid by 0.067, okay, it's below the centroid by 0.067, or from the top CB by 1.067. So this is the vertical component, you can see it here, okay, YCP. Then the horizontal component, which is XCP, we now use the moment. Okay, the XCP for the vertical force is found because this YCP it shows the point of where the pressure force is acting. Okay, where the pressure force is acting in the horizontal direction. Okay, which is this one, FH. What about the vertical component? We need to find the XCP by taking the moment about any point about point C. When we take moment here, it will be the force FB times XCP. XCP is here. This is where XCP lies. Okay. And then since we know YCP, so when we take moment about point C, it is going to be moment due to the vertical component Fy times XCP. Okay. MC, and then this should be equal to the moment due to all the vertical moment, because this is Fy. Fy is sum of all the vertical forces, okay, weight and Fv. Okay, so moment due to Fy will be equal to moment due to W and Fv. Okay, so xcp times fy will be equal to fv times the distance is 1 because from here to here is 2. So it will be acting at the centroid because it is vertical. Remember, for vertical, if it is horizontal, if the surface is horizontal, the pressure force will be acting through the centroid. But if it is vertical or inclined, then it will be acting through the center of pressure, which is not the same as the centroid of the surface. Okay, so but here it will be acting through the centroid because for the vertical force is acting on horizontal plane. Then W, the weight, okay, the weight in this case will be acting through the centroid of the body. Okay, the centroid of a quarter cycle, the formula for the centroid is 4r over 3 pi. Okay? If it's the rectangle is passing through just the middle point, but for a semicircle, this is the formula for the centroid. Okay, so once we find x bar w, we substitute it here and find xp. So xp, which is the x component, okay, is now 0.957, which is presented in this figure. So now we have fy, this is fy, and we have fx, and then we can find the resultant force. Okay, we can find the resultant force. The resultant force is simply we have shown is the square root of fx plus fy all squared. Okay, and to find the angle through which it is acting, that's its line of action, use theta, tan theta. Okay, tan theta in this case, which is opposite, is going to be fy over fx. Fy over fx. Okay, and theta is now 48 degrees Celsius. I hope it is clear. Okay, this is a very simple example to demonstrate the application. I mean, how to find the hydrostatic force acting on a curved surface. And you need to understand all the steps very well. Okay, is it clear? So now, if this is very clear, now let's have a short concept quiz, which says, determine the magnitude, direction, and line of action of the vertical and horizontal components of hydrostatic force acting on the surface. Okay, the surface here is AB. Determine the resultant hydrostatic force on the surface. Okay, so the surface is 1 meter long. Okay, normal to the page. Okay. It's 1 meter long, normal to the face, and the radius is 1 meter. Okay. So now let's start. Okay. The height from the water table is 1 B. It is 1 to B. So this, as usual, we need to find the horizontal and the vertical components of the force, the forces of the resultant force, and then evaluate the resultant force. Okay. So I will leave this to you to try. It will demonstrate whether you really understood this one. Okay, it will test your understanding of this example. But you actually need to do this. Okay, you need to do it. Now, we'll start another topic called buoyancy, which is very important. Okay, buoyancy. It is a common experience that an object feels lighter and weighs less in a liquid than it does in air. When you weigh a substance, okay, in air, let's say it weighs, let's say you have a block, let's say 10 kg. When you weigh it in air, it weighs 10 kg. When you immerse it in a container filled with water or a liquid and weigh the same block here, it will weigh less. Okay, let's say it will weigh 7 kg. Let's say its weight in liquid is 7 kg. So how did you lose the weight? I mean, where is the remaining 3 kg? Okay, where is the remaining 3 kg? Does that mean matter can be created and destroyed? Did you destroy the mass? No, you definitely did not destroy the mass. Okay, you definitely did not destroy the mass. Okay, this object, 10 kg, when you immerse it in liquid, if this is the initial level of the liquid, when you immerse it inside, the level will rise definitely because the object will displace the liquid. Okay, will displace equal volume, would displace its own volume in the liquid in which it is immersed. Okay, so the volume might increase to this point. Okay, this is the initial level, this is the final water level. Okay, so this amount of liquid, if this is open, you can put it in a container. Okay, you can collect it in a container and you will realize that the volume of the block is equal to the volume of the liquid displaced. Okay, liquid displaces a body when immersed in water, it displaces its own weight in the liquid in which it is immersed. Okay, now this is one thing. The other thing is the fact that liquid or water in particular, it has a force, a vertical force acting upward, an upward vertical force that is acting on all bodies, immersed, partially or wholly immersed in them. Okay, when you immerse any object in water, there's a vertical force acting on that body. Okay, which is like a way of, it is like supporting, trying to push it up. Okay, you have weight W acting, and then you have acting vertically downward, the weight, and then you have another force in opposite direction acting vertically up, trying to push it up. We are going to examine the equilibrium, I mean what transpired, because what transpired if the vertical force, which we call the buoyant force or upthrust, FB, okay, we call it the buoyant force, which is the vertical upward force acting on all bodies immersed in liquids. Okay, we'll examine the statics, the equilibrium of these two forces. When the buoyant force is greater than the weight, what happens? When the buoyant force is equal to the weight, what happens? When the weight is now greater than the buoyant force, what happens? Okay, so this buoyant force, which emanated from the liquid, is what is responsible for the decrease in the weight inside the liquid. Okay, it weighs 10 kg outside, but in the liquid it experiences some loss of weight, so it came down to 7 kg or let's say approximately 30 Newton. Okay, is because of the upthrust. The upthrust is more or less like supporting. It is giving a support to the body inside the liquid. Okay, and that's why the weight reduces. Okay, that is why the weight reduces if it is inside a liquid. Okay. Now, this can be demonstrated easily by weighing a heavy object in water by a waterproof spring balance, which I just finished explaining here. Also, objects made of wood or other light materials float on water. Okay, objects made of wood or other light materials float on water, and these and other observations suggest that a fluid exerts an upward force on a body immersed in it. Okay, so explain. We are going to explain why objects float and why do they immerse. I think this I explained before when talking about density. Okay, when the density of the body is less than the density of water or the liquid, the body floats. If the density is equal, then it will sink into the water. If the density is greater than the density of water, then it will sink up to the bottom. Okay, it will go to the bottom because heavier objects settle down, okay, and lighter objects, go up. Now, this force that tends to lift the body is called the buoyant force or upthrust and is denoted by FB. Okay, we call it buoyant force. Buoyancy is simply the act of lifting something up. Okay, floating, the act of floating. Okay, pushing something up. Okay, to the surface. Okay, it's an English word, buoyance. Okay, so it's called buoyant force or upthrust. Upthrust because it's a thrust, okay, like a pressure force, but active, pushing, okay, pushing upward, vertically upward. Now, the buoyant force is caused by the increase of pressure with depth in a fluid, okay? The pressure increases with depth. And consider, for example, a flat plate of thickness H submerged in a liquid of density rho F. Rho F is the fluid density parallel to the free surface as shown in the figure. We'll look at the figure now. Okay, this is the figure. You have a plate, okay, submerged in fluid. Okay, the density of the fluid is rho F. Okay, the area of the top and also bottom surface of the plate is A, so it has the same area, and its distance to the free surface is S. Okay, distance to the free surface is S, and the thickness of the plate is H. Now, let's evaluate the gauge pressures at the top and bottom surfaces of the plate. Okay, the gauge pressure, that's the pressure above atmospheric, acting on the top as well as the bottom. Okay, at the top is going to be the pressure due to the height of the fluid. Okay, whose distance is S, isn't it? So we have rho G, and the pressure force we multiply by the area. Okay, the pressure force. So this gives the pressure force acting, and then from the bottom, the distance has increased due to the height H. Okay, the thickness of the plate. So instead of S, we have S plus H. Okay, so this gives the pressure force from the bottom. Okay, and then when we now, the buoyant force is now the resultant force acting on the body, and the resultant force is now going to be the summation, okay, the algebraic summation. Okay, if we take the vertical to be positive, okay, so F, the force acting at the bottom minus that at the top, which will give us, okay, rho F G H A, okay. HA is the volume of this plate. Okay, is the volume of this plate. Okay, so it's rho GV now, okay, which is simply gamma V. Okay, but now V is, if you look at V again, is the volume of the liquid displaced by the plate. Okay, this rho GV is simply the weight of the liquid. Okay, simply the weight of the liquid whose volume is equal to the volume of the plate. Okay, whose volume is equal to the volume of the plate. Okay, what are we saying here in essence? We conclude that the buoyant force FB acting on the plate is equal to the weight of the liquid displaced by plate. Okay, is equal to the weight of the liquid displaced by the plate, because this rho GV is the weight of the liquid displaced by the plate. Okay, it is not equal to the weight of the plate because this is rho F, not the density. This density is for the fluid, not density of the plate. If it were to be the density of the plate, then we can say it's equal to the weight of the plate, but it is not. Okay? It is not, but it is exactly equal to the weight of the liquid displaced. Okay, like I demonstrated here. When you insert this block, 10 kg, it weighs 7 kg here inside the liquid, then 3 kg is displaced, isn't it? 3 kg does about 30 Newton. So it means the upthrust, the buoyant force is equal to 30 Newton. It's exactly equal to the weight of the liquid displaced, okay, which is 30 Newton. 30 Newton of liquid is displaced when you immerse 10 kg, 100 Newton inside liquid, okay? So it weighs 20 Newton. So the remaining 30 Newton is because of the upthrust, okay? So the upthrust is what is holding, giving support or taking care of the deficit or the difference in the original weight of the body when it is weighed in air, okay? We are going to explain later because air is also a fluid. It's a fluid. So we should experience even some upthrust, some buoyant force in air. But because, as we have seen in the formula, the buoyant force is directly proportional to the density of the fluid. Air, the density of air is very small, 1.2 kilogram per meter cube. That of water is 1,000. So that's why the buoyant force in air is very small, although it also has some application. It has some application, practical application that we are going to explain, like in the hot air balloon. You know, the hot air balloon is using that. Okay. So now the buoyant force is equal to the weight of the fluid displaced. Okay. So buoyant force acting on plate is equal to the weight of the fluid displaced by the plate. So here we conclude. Also, we come to the conclusion that when an object is fully or partially immersed in a fluid, it displaces the fluid, okay? It displaces on volume in the fluid in which it floats, because the volume of the body or the object of the plate, let me say Vp, is equal to the volume of the displaced fluid, okay? The volume of the plate is equal to the volume of the liquid that is displaced by the plate, okay? So that is why HA here is equal to V. HA is the volume of the plate. V here is the volume of the liquid displaced, okay? Then is the weight of the liquid displaced when it is fully immersed in water equal to the weight of the body? That is something we are going to explain by considering some scenarios later in a few slides to come. Now, for a fluid, here I already explained that you can see the buoyant force increases is proportional to the density of the fluid, meaning if a fluid having a liquid that whose density is higher, let's say, than water, will have more buoyant force, meaning it can support even heavier objects, or it will make heavier objects to some kind of lose some weight in them when they are fully immersed. Okay. For fluid with constant density, the buoyant force is independent of the distance of the body from the surface. Okay. You can see that the buoyant force B is simply the density of the fluid G times the volume of the displaced liquid. Okay, so it is independent on the distance S. Okay, the buoyant force is independent on the distance. The body is independent of the distance of the body from the free surface. Okay, It doesn't depend on this distance from the free surface. Meaning, once the body is fully immersed, okay, once the body is fully immersed in water, then the buoyant force is constant throughout, okay? The buoyant force remains constant throughout. Then we are going to also examine another scenario in which we find this may be called the limiting buoyant force or the maximum buoyant force, because the buoyant force has some kind of range, let's say minimum and some maximum, just like the case of, let's say, frictional force. If you remember in statics, in friction, when you have two bodies in contact, when you have a table, when you have a block which is being pulled by a force P, okay, frictional force is acting on the surface to oppose the relative movement of this block, okay. So when the block is at, say, the weight of the block now is W, okay. So when a force is applied to move the block, okay, frictional force will set in, and then as you are increasing the force to push the block, the frictional force increases. But then the frictional force has a maximum, okay? It is called the limiting frictional force, okay? It reaches maximum. And from this point, any increase in P will now set the block in motion, because it means the applied force has overcome the frictional force. The frictional force is like a force trying to prevent the relative movement of the block. Okay, so once you apply P greater than the frictional force, then that is the only condition when the block will be in motion. Okay, so this is the limiting frictional force, the maximum frictional force. So once P is greater than this value of the frictional force, okay, or the limiting frictional force, okay, so once it is greater than F, okay, then the block will be in motion, and then the value of the frictional force will begin to reduce because it is in motion. Then you will now have dynamic frictional force. Before you have static frictional force, and this is the maximum value of the static or the limiting frictional force. The same thing with the buoyant force. Okay, the same thing with the buoyant force. When an object is floating on the surface of the liquid, the buoyant force is not at its maximum value. When it is immersed, as soon as the object is fully immersed, then that is when it will attain its maximum value. But once the object is fully immersed inside the liquid, then the buoyant force do not depend on the distance from the surface of the liquid at all. Okay, it only depends on the volume of the displaced liquid. Okay, because this is constant, the specific way, which is rho g. Okay, this is a constant. So the only variable is the volume of the displaced liquid. Now it is also independent of the density of the solid body. Okay, the buoyant force is also independent of the density of the solid body. It depends on it only depends on the density of the fluid itself. Okay, it depends on the density of the fluid itself. Although density, as we are going to see later, as we are going to examine, it plays a big role as to whether a solid body, floats on top of a liquid or sinks. Okay, this we explained before, and we're going to explain with some diagrams. Now, this is generally known as the Archimedes principle. Archimedes is a Greek mathematician who lived even before the coming, before Christ, 287 to 212 before Christ. Before Christ, that is Prophet Isa alayhi salam. Okay, and what is the Archimedes principle? Okay, it says that the buoyant force acting on a body of uniform density, immersed partly or fully, meaning whether it is floating with some of its volume immersed in the fluid or it is fully immersed in the fluid. Okay, so that the buoyant force acting on this body is equal to the weight of the fluid displaced by the body, and it acts upward through the centroid of the displaced volume. Okay, the buoyant force, the resultant buoyant force, okay, acts upward. So direction is always upward. Okay, it is always upward, and it acts through the centroid of the displaced volume. Okay, so this is its line of action. So this is the statement of the Archimedes principle. Okay, the buoyant force acting is equal to the weight of the fluid displaced. Okay, and acts through the centroid of the displaced volume. Now, still explaining the Archimedes principle, an object here is buoyed up by a force equal to the weight of the fluid displaced. Buoyed up, meaning it is pushed up by what? By the force of the upthrust. Okay. In air, this object weighs 7 pounds. 7 pounds. Okay. When you immerse it in liquid, okay, in water, it weighs only 4 pounds. Meaning it has lost 3 pounds. Okay. These 3 pounds, when you immerse it, it will displace the liquid. It will displace its own volume. Okay, so when you have a container, when you immerse it inside, the level will increase. If this is open, water will gush out. Okay, because the object has volume and it has to displace its own volume inside water. And if you weigh this water, you will realize it is exactly 3 pounds, meaning the balance of the weight. Okay. This 3 pounds is exactly the upthrust or the buoyant force acting on this body when it is fully immersed in water. Okay, this is the buoyant force that acts upward to cancel out part of the force. Okay, so it is more or less like providing support for objects immersed in liquids, okay, or in fluid. Now, let's say something on floating bodies. For floating bodies, okay, and this applies to anything floating on water, let's say ships, boats, you know, and all that. Okay, the weight of the entire body must be equal to the buoyant force. Okay, when an object is floating, like in this case, the weight of the body, there is equilibrium here. Okay, by floating, it means the body is in static, is assumed to be in static equilibrium. Okay, so the weight here acting is W, and the buoyant force experienced by the weight is FB. Okay, so you can assume this to be a ship that is partially submerged. So this is the submerged area. Okay, it is partially submerged. So now the weight of the body, when you take equilibrium, I mean, this is the free body diagram. If you want to apply the equilibrium here, so the sum of forces in the vertical direction to be equal to 0. So you will realize that the buoyant FB is equal to W, meaning the force of the buoyant force is equal to the weight, the total weight, not the submerged weight, is equal to the total weight of that object. Okay, it's equal to the total weight of that object. This is analogous to, let's say, this is your palm. No, let me say, this is your hand holding, let's say, 1 Newton. Okay, if you hold 1 Newton here, it means you have to apply 1 Newton to be able to hold it, because 1 Newton, the weight acts downward. It needs to be acted upon by equal but opposite force. Okay, according to Newton's third law of motion. Okay, equal but opposite force. Action and reaction are equal and opposite. Okay, so you need to, if you have 1 Newton, you need to apply 1 Newton to be able to hold it. So if this is floating on water, it means it is completely being held by the water. Okay, and the force that is holding the body is the buoyant force. Okay, so the buoyant force is equal to the weight of the body. Okay, it's not just equal to the weight of the displaced, of the submerged body, okay, but the total weight of the body. Now, this area, this is the volume. This volume will represent the volume of the displaced fluid. Okay, this shaded area will represent the volume of the displaced fluid. Okay, so the submerged volume is equal to the volume of the displaced fluid, while the upthrust in this case is equal to the weight of the body. Okay, so FB is equal to W. Okay, and then here we use the volume of the submerged body. Okay, not the total volume of the object. We don't use the total volume of the object in this case. We use the volume of the submerged area, okay, or the volume of the liquid displaced. Weight is given by the average body weight, and here the volume is the total volume of the body, okay, which is, this is our weight, okay, and this is the buoyant force. So now from this you can strike out, G is the same. Okay, so the fraction, the submerged volume is given by the ratio between the body, the density of the body, and the density of the fluid. Okay, and the density of the fluid. Therefore, the submerged volume fraction of a floating body is equal to the ratio of the average density of the body to the density of the fluid. Okay, the density of the fluid. Note that when the density ratio is equal to or greater than 1, the floating body becomes completely submerged. Okay, when this ratio is equal to or greater than 1, the floating body becomes completely submerged. Because if it is equal to 1, it means that the submerged volume is equal to the total volume, meaning the body is totally submerged. Okay, so it means it is going to go under. Okay, like in this case, like in the third scenario here. Okay, now still explaining this figure, when the weight of the body increases, okay, assuming the weight of the body increases, then the submerged area will increase as well. You can see in the second figure. But here the upthrust in the second case is higher. As indicated by the arrow, it is higher. Okay, when the weight increases, it displaces more liquid. Okay, hence the upthrust acting on the body increases. This will increase up to a point, up to the third phase, when the body becomes fully immersed in the fluid. Okay, it's fully immersed in the fluid. At this point, you have the maximum upthrust, or the buoyant force, FB, is maximum at this point. And it cannot get bigger in this case. Because remember that the buoyant force does not depend on the depth to which the body is immersed. It's fully immersed in the fluid. Okay, so at this point, the buoyant force is the same. Let me call FB1, B2, B3, and FB4. Okay, when you increase the weight further, this W1, W2, W3, W4. W4 is greater than W3. Then the body now can go down up to sinking to the bottom. Okay, but the buoyant force remains the same. Because once the body is completely immersed in the fluid, the buoyant force will attain its maximum value. Because that is a point when VD is maximum. That is the volume of fluid displaced. Okay, the displaced fluid here, VD3, is the same as the displaced fluid here, VD4. Okay, and the upthrust is equal to the displaced volume of the fluid. While in this case, the displaced volume is less than the displaced volume here. Okay, but once it is immersed, then the displaced volume do not increase irrespective of the depth to which the body is immersed in the fluid. Okay, my time is up. Okay, tomorrow we will continue from here. Do you have any question before we call it a day? So I have 13 guys. 2 guys are absent. All right, see you tomorrow then. And tomorrow we will have quiz. Okay, I mentioned the specific slides, okay, that it is going to cover.